cathode, then we have the collector on the other side, and an electron beam is flowing along from the cathode through to the collector. And you have your signal flowing in this pretty much a square around it. And yeah, that's the concept diagram of the BWO. There are two main subtypes, that is the M type and the O type. And then they have certain specifications where the O type has its range of 1 megawatt at 1000 gigahertz and 50 megawatt at 200 gigahertz. And they're used with the powerful and stable sources of microwave frequencies. And it also has a good quality wavefront that will attach below. And yeah, they are found for imaging. You'll get to see the applications later. This is a miniature. This should be the type, the miniature O type, and this is the one that was developed in the 50s, 1952. Yeah, or 56 actually. So this is just a miniature of the O type BWO, the O type backward wave. It looked something like this, but there are larger ones that are there, and it has pretty much evolved over time. So how does BWO work? And I've divided into some certain stages. I hope you still remember this concept diagram. You'll bear in mind the concept diagram of, it's also found in Wikipedia actually, where it's the electrons, I'll repeat, move from the cathode to the collector, and then your signal is passing in this red path, input, output. So have that in mind. So the BWO will start with the electron beam and the slow wave structure. And if you remember from TWTs that we talked about in our most recent previous class, yes, BWOs, they utilize the electron beam and the slow wave structure, because remember it is in the family of TWTs, and the slow wave structure, which can take the helical. Last time Kelvin showed us a picture of the helical TWT, like a helix or a series of coupled cavities. The BWO is designed to slow down the velocity of the microwave signal, or this structure is used to slow down the phase. The backward wave oscillator gets its name from its property of the wave being a backward wave. So they differ from TWTs in that the TWT, while it has the forward wave, the BWO has a backward wave. And yeah, so a backward wave is a wave whose phase velocity is opposite to the direction of energy flow. So that's also in part something to note, what a backward wave is. Energy transfer and oscillation. As the electron beam travels through the slow wave structure, it interacts with the backward wave. If the beam velocity is slightly higher than the phase velocity of the backward wave, here you're talking about the interaction between the electron beam and your signal. So if the beam velocity, the electron beam, is slightly higher than the phase velocity of the backward wave, energy can be transferred from the electron beam to the wave, leading to wave amplification. Since this interaction occurs with a backward wave, the amplified signal travels back towards the electron gun, forming a feedback loop that sustains oscillation. So we'll get to review these things later. Frequency tuning. One of the key advantages is the wideband tunability. The frequency of oscillation is controlled by adjusting the electron beam voltage. The beam voltage causes an increase in the electron velocity, which in turn allows the beam to interact with backward waves of higher frequencies. And thus we have tuning of the oscillator's output frequency. Some of the applications I found these three fields. And remember, we talked about its advantage being a wide tunability frequency band, and the applications are in signal generators, and where they are used as sweep oscillators and signal sources in test and measurement equipment that require that wide range of frequency. It's also used in spectroscopy, and in spectroscopy they are used for analyzing the absorption and emission of EM radiation by materials, and also in frequency agile radar, where we have rapidly changing frequencies, and the BWOs serve as frequency agile local oscillators. Practically, where I found, say, an interesting thing is in this slide that I'm sharing. Noteworthy. Casinotrons, which is the other name of BWOs, are used in research, civilian and military applications. For example, the Czechoslovak Kopach passive sensor and Ramona passive sensor air defense detection systems employed casinotrons in their receiver systems. This is a real life application. The Czechoslovak Kopach passive sensor, and it was applied in electronic warfare, where they were used to detect, I believe, should be bombs that were impending, and they used the time difference of arrival, and they could take they could make detections in, is it 3 or 6, 3 different locations at the same time, 6 different locations at the same time, and each of those locations they would take 3 measurements. So yeah, that's how it's an interesting thing. So remember, BWOs, also known as casinotrons, BWOs, backward wave oscillators, and TWTs, transverse wave tubes. So the differences, I noted these 4: the interaction of the wave, the signal direction, the oscillator stroke amplifier, and tunability. As I have already highlighted before, the BWO makes use of the backward wave, where we defined the backward wave is where the direction of the wave is different from the direction of the energy of the wave. So that was what we call the backward wave, and the forward wave is now the opposite, in that the same direction of the energy wave is the direction of the signal direction. Remember from the drawing that the amplified signal travels towards the electron gun. I'll just go back to that slide again. So you can see here in the BWO, this signal is going in this direction towards the left of this slide to the cathode. And you can can tell that quickly. So here in the BWO, as I've said, the signal travels towards the electron gun, while in the TWT, the amplified signal travels the same direction as the electron beam. If you recall, we were talking about bunching and all that in that side. The oscillator stroke amplifier here in BWO, it is used as an oscillator due to that inherent feedback from the backward wave, and the TWT is used as an amplifier. Yeah, so that's also another difference. And in terms of tunability, also there, the BWO is widely tunable, with its range being a large range. Yes, is someone trying to speak? Yes. Okay, so the TWT is not easily tunable. That's also something to note. And out of what I've given, I've not gone in depth. Yes. Um, this is just a general surface knowledge of BWOs. If you're interested, you can go to some straight up sources that talk about BWOs. Majorly, I found the book on electronic circuits and devices, having detailed also the graph work of this thing and its behavior. You can also try and look into that. So for me, I see asking questions would pretty much help in understanding. So the first question that these are some of the questions, 1, 2, 3, 4, 5 questions that I found would help us to understand. What is the fundamental operating principle of a BWO? How does it differ from a TWT? What are the key components and structure of a BWO? How does the interaction between the electron beam and the electromagnetic wave occur in a BWO? What are the advantages and disadvantages of BWOs compared to other microwave devices, including TWTs? What are the typical applications of BWO? And yeah, I also compiled their answers as well. So, but if you need to review, these are some of the questions you might you might need you might need to ask yourself concerning the BWO. For the first question, what is the fundamental operating principle of a BWO? How does it differ? We talked about that concept diagram of the cathode and the collector and the tube where the signal is passing through input to the output. So BWO, as just to review, is a type of vacuum tube that generates microwaves by converting electron beam energy into electromagnetic radiation. The principle is the interaction between the electron beam that is passing from the cathode to the collector and the slow wave structure yenye ilikuwa inaonekana as a square, which causes the backward wave to travel in the opposite direction. Furthermore, the operating principle, we talked about it already. You can review it in your own time, and also the differences, the same ones that we talked about. And that's also part of that. So the second question, which asks the key components and structure of a BWO. And here are the main parts. It contains it has the electron gun, which is used to generate the electron beam, and also it contains the slow wave structure. So those are, and also the collector. Those are the three components. Am I missing one? Yeah, and also the focusing coils are also make part of the BWO. Also the output coupler, the tuning mechanism. Yeah, so those are some of the parts that make it up. They make up the BWO. Also, one of the questions, the interaction between the electron beam and electromagnetic wave in a BWO. How does it look like? Remember, we talked about the backward wave. So that's from its name, backward wave. So the electron beam interacts with EM wave in the slow wave structure, leading to generation and amplification of high frequency microwave radiation. And that's the interaction, asynchronous, and it allows for asynchronous interaction between the wave and electron beam, which is essential for energy transfer. And also those are things that you can get time and look at wave amplification. Yeah, that's getting in depth. So I'd like us also to look at these advantages and disadvantages of BWOs compared to other microwave devices. So the first advantage, which I think should be the main advantage of the BWO, is this wide frequency tuning range. You find that the TWT on the other side, it does not have this tuning range, but for BWO, it has this wide tuning range, which allows for its application in spectroscopy or spectrum analysis or other systems. So you can always remember that. Yeah, the compact size that it has. You remember the one that was we looked at earlier, that could be held in the hand. The O type, the O type, the O type BWO. You can remember that its compact size serves also as its advantage. So portability, space, yeah. So high power frequency at certain frequencies, you find that is also useful. Simple design, uh, and the disadvantages is now the lower efficiency compared to the TWT. The TWT is more efficient than the BWO. The limited power output, tendency to oscillate, designed as an oscillator. It serves also, while it's a good thing, it's also its shortcoming. It tends to be unsuitable where we are talking about stable amplifications. If we were to require stable amplification, count BWO out. So thermal stability, yeah, that's also a shortcoming due to thermal drift. And this is owing to the fact that the interaction between the slow wave structure and the beam voltages uh, changes variably. Yeah, so there are also advantages of TWT over BWOs. So I believe that's something you can also look at. High power output, forward wave amplification, without oscillation, broadband performance. Yeah, and also the disadvantages of TWT are there, larger and more complex. Yeah, so in summary, this is now what makes the characteristics, uh, the pros of one and the cons of the other. So a wide tuning range is the pro of BWO. A lower output power, it is less efficient. Uh, it's used as an oscillator, compact and simple design, prone to frequency drifts and thermal drift. Yeah, so those are things that you can keep in mind. Yeah, The other question, which was the last question, the typical applications of BWOs, which the first one is in electronic warfare. I believe that's what it was created for or invented for. So they are used to generate high power microwaves for jamming and disrupting enemy radar and communication systems. So I believe some of us might find application in that. YBWO, their frequency agility makes them ideal for quickly tuning across a broad frequency range, which is essential in electronic warfare for countermeasures and signal jamming. So the general application in electronic warfare, radar jamming, communication signal interference, and counter radar systems, because we see it's an oscillator, so it can disrupt those amplifications. Radar systems, BWOs, are as microwave sources in radar systems, particularly in millimeter wave radars. Why BWO in these radar systems? BWOs can generate high frequency signals and allow for fine frequency control, making them suitable for these systems. And the application in radar systems, short range radars, weather radars, military radars, and radar for automated uh, vehicles, collision avoidance systems. Spectroscopy, yeah, BWOs in millimeter and microwave wave uh, spectroscopy for analyzing molecular and atomic properties. Here, the continuous frequency tuning is used for scanning different frequencies and studying the absorption and emission characteristics. And the applications here now in spectroscopy, they find use in analysis of gases, plasmas, molecular structures, and now this is scientific research and laboratory works. Millimeter wave communications, we've talked about it previously a number of times. So the BWOs serve as frequency generators for high frequency communication systems. And why BWO in this case? Their ability to generate stable and tunable microwave signals makes them useful for high frequency communication links, especially point to point. Here now, application use is in military communication links, satellite communication, and microwave transmission systems. Plasma diagnostics is something we've talked about in spectroscopy also. The device ability to generate high frequency. So if you can tell that most of these applications make use of the wide frequency tunability range, so and also its ability to generate high frequency. Uh, yeah, as I've said, to measure electron densities and plasma wave interactions. Here in fusion research, space physics, and other plasma related studies. We are close to the end. Terahertz imaging and sensing. This also another one for security scanning, medical imaging, and destructive testing. BWO's ability to generate millimeter and sub-millimeter waves makes them suitable for high-resolution imaging and sensing in the terahertz range. They find application in airport security scanners, industrial control, industrial quality control, medical diagnostics, and scientific imaging. So you can see that so far the BWO is finding application in in so many, even from the post-war period even to modern age times, because in the post-war we are talking about electronic warfare, the Czechoslovak Kopach passive sensor and the Ramona sensor as well. And also in our times in the airport security scanners, you can find the WOs finding their use in medical imaging. They find use in radar jamming, signal jamming. They found their use. So pretty much they are they are they are found in time past and also in time present. Research and development. BWOs are commonly used in research laboratories to generate tunable microwave signals for experiment setups. Why BWO in this case? The ability to produce coherent, high frequency, and broadly tunable waves. We find that that is the recurring reason that they have this great ability uh, to generate that, and they find application in experimental physics, microwave electronics development, and material characterization. Um, yeah, so this also a summary of what we've looked at: electronic warfare, radar systems, spectroscopy, millimeter wave communications, plasma diagnostics, and also research and development that couldn't fit in the screen. Yeah, so um, so they are found in this so many applications in present time and also in the time past. And remember this image that is as I close. Remember this image that shows the BWO. And recall it that we have the cathode that generates the electron beam, shooting them across all the way to the collector. And we also have this slow wave structure that looks like a square and has its inputs. Your signal flows in, flows up, flows down, and across and up. And the interaction between the electron beam that is flowing in this direction and the signal in the slow wave structure now causes oscillations. That's the basic principle, just to explain it in layman's terms, that the oscillations are caused in that sense. And now its properties to generate high frequencies that are tunable over a wide range of frequencies, makes it to find applications in a lot of things. And the note given here in terms of the red signal flowing from the input traveling through the waveguide to the output, and notice that the signal opposes the direction of the electron gun, which is in the opposite direction to the traveling wave tube. And the backward wave oscillator is so because of signal is opposite to the direction of the energy wave. So yeah, that's the BWO in general sense. And we've come to the close. That was group 3. This was our last thing that we were to present. We have presented in this should be our third session. And yeah, we have closed it at BWO. Is there any question concerning the BWO? Is there any question? Let me review the chat if there's any question in the chat. There's no question in the chat. Is there any question concerning the backward wave oscillator or the TWT, the transverse wave tube? We can address. Okay, since I've seen no one unmute, thank you for listening. I'm seeing in the chat, George Mwangi is asking, can you explain how the oscillator? I believe it's a question that Haijaisha. George, you can finish the question. how the oscillator can you explain how the oscillator oscillations is achieved by the feedback? I think I can just bring back the slide to that point where we talked about that. Yes, that's a good question, by the way. That's a good question. It was here where we're talking about we talked about feedback. Let me just go to that slide. Yes, energy transfer and oscillation. So just an overview, as I've said, I hope you remember the direction of the electron beam and the direction of your signal and all that. Now, here in energy transfer and oscillation, what I gathered, as the electron beam travels through the slow wave structure, it interacts with the backward wave. If the beam velocity is slightly higher than the phase velocity of the backward wave, energy can be transferred from the electron beam to the wave. Hope to that part it's clear, which leads to wave amplification. Since this interaction occurs with a backward wave, the amplified signal travels back. I hope that part you are underlining, since this interaction, the interaction between the electron beam and your signal, since this interaction occurs with a backward wave, the amplified signal travels back towards the electron gun, forming a feedback loop which sustains oscillations. So the question about I hope I'm addressing the right question, but the question about how the oscillations and feedback. So there's a feedback loop that you're talking about. That is, from this interaction, the amplified signal is brought about due to the interaction between the electron beam and the signal that you have put into that slow wave structure. And this interaction leads to an amplified wave. This amplified wave travels back towards the electron gun, the cathode that you saw. And now this forms a feedback loop that sustains the oscillations that occur over and over. So yeah, that is clear. That is clear. Yeah. So yeah, it's pretty interesting, but for myself, I did not cover in depth, but you can take time and check the book I recommended, Electronic Devices and Circuits, if you wish to look at the graphical work of this oscillator and also visualize using words how it works. Yeah, so that's the end.
Okay, great. Thank you. You guys, you know I'm on strike. I'm not supposed to speak. Where's Sherry? Is it Seraphine? Eric, don't laugh, man.
Yes.
Seraphine, I don't want to be a traitor. Can you moderate the class? So you said you have the cut on 19th, eh?
Yes.
So today I will send the tutorial.
Mm.
Yeah, we have to discuss the tutorial before you sit for the seat.
I think we can move to group 4.
Hello, can you confirm you can hear me?
Yes.
Okay, my presentation is on force attractance theorem. I should start first. Okay, this is the presentation I've prepared. I should start first by explaining what force attractance theorem is. Basically, it is the description of the suscitance and the admittance on with regards to frequency, whereby we can say that the frequency increases monotonically with frequency. The presentation here is focused on how we can prove this fact. And since it's equations, I wanted us to do it together so that we can move together. So yeah. Okay. First, we can start by considering a one-port network with the termination T, so that the voltage here is V plus and I plus, and then the voltage coming through here is V minus and I minus. This is a reactive termination. The field that specifies here is the Maxwell's equation that we used, so that we learned last year. It's negative J omega UH, and H is equals to J omega E. We shall take the derivative with respect to W of the complex conjugate of these two equations. The conjugates, that is the complex conjugates, it's J omega UH, and so this is, and then we take the derivatives of these two equations, such that our equation will look something like I hope you can see what I'm doing here. I'm using basically the product rule of differentiation, whereby this J is our constant, and then our factors for differentiating is omega U and H. So this will be the result for the first one, and then for the second one, it will be negative J omega E. Sorry. The next step was supposed to consider two specific equations. The first one is this one, H, and then the second one is this one. We expand it using the vector identity such that A cross B is equals to this cross A, B minus A, B. So such that this is our A, this is our B for the first two, and then so our result will be this stroke E, and then our second one. From here we can see we have these two terms. For example, this term, this term, this term, and this term. We already found it here on the first part. So when you simplify these parts, it will, okay, we're supposed to basically to replace the values here, and then when you simplify, we'll get something like J. H dot H. And then for the second one, get J H. Okay, so from here we can look at the terms having these specific terms, this one and this one. We can note from the Poynting's theorem that we suppose this should define the power. We should look at the real part. Since this is the imaginary part, the J, this whole part vanishes. So such that we can have these two having basically these equations only, and then when we sum up these two equations, we get this stroke E cross. Okay, we get J H. Okay, now this is the part that will be used. This is the part that will be used to find the first subtractance theorem. Okay, so when you consider this termination volume, and then we integrate across that path and use divergence theorem here. We can use divergence theorem. Divergence theorem states that this V, the dot product of F dV is equals to S F dA. I hope you can all remember this. Okay, so the equation becomes S E plus H okay, sorry. Okay, from here we can notice there are two things that we were taught last year. We have the energy representing the magnetic field and the energy representing the electric field. The energy representing the magnetic field, we can define it as Wm. It will be given by a quarter of V H and the energy representing the energy in the electric field should be a quarter V dV. So in this equation, in this first equation, you can replace it with these two equations basically. When you replace it with the two, it will become negative 4J Wm plus We. Hope you can all see. Hope you can all see where this is coming from. Yeah, so this is it. This is okay. This is the energy in the volume. The volume that we're talking about is for a termination that looks for a one-port network. A one-port network, for example, can in a 3D representation can look something like this, such that the volume of termination is like this whole surface here. So this is the whole surface that we're considering that we're considering. We have N stroke E and N cross this one. They vanish across the perfectly conducting waveguide walls. The surface integral reduces to an integral terminating on the plane T only. Remember this, the plane T is only this part here. On the plane T only. On the terminating plane, we have this equation here. I think I can. We have this equation so that E cross the derivative of the conjugate of H plus the conjugate of E cross H and ds is equals to V, the derivative of the conjugate of I plus the conjugate of II. This is where V is the terminal voltage and I is the terminal current. For lossless termination, a lossless termination are considering the ones that don't have the resistance or the resistance values. um, so such that the V is equals to Jix. When we integrate, when we find the complex conjugate of this and integrate with respect to W, we'll get negative Jx integral of I of the conjugate of I minus Gi in derivative of X. Remember this, we're using the same product rule. Combining these two and taking XW as the subject, we get this equation. And for I is equals to JBV, we get this equation. Now, from these two, we can notice that the equations are positive. This shows that this is actually the proof of the reactance. This is actually the proof of the reactance theorem. When you plot X against B for frequency, it gives the following graph. This extra information here is just extra information to help understand these equations better. In particularly, we note that the slope of the reactance is always positive. That is, the derivative of X is always greater than 0. This positive slope condition means that the poles on zeros of X must alternate as W increases from 0 to infinity. This general property of the one-port reactive circuit is known as the Foster's reactance theorem. This same equation, Sherry will show like the longer version of the X equation. This equation we can prove this relation here by looking at how the poles and zeros correlate with each other. We're using the Taylor series, and then we're taking the derivative with respect to and replacing this W with WO. We'll get A1. So we can, from here, we will have x0 is equals to A1, such that X has a simple 0 at W0, B has a simple pole at W0. The zeros of B are simple, the poles of X are simple. All these are just to explain like more about this graph here. Okay, now we can look at how it affects the Foster's first form and Foster's second form and its effects on losses. It's the same way. The Foster's first form, we were looking at the inductance, the impedance values. While the second form, we're looking at the admittance values. For first form in the loss free case, if the polynomial function has a pole at W0, W is equals to 0, one of the LC sections will be reduced to a single capacitor, and if the polynomial function has a W is equals to infinity, one of the LC sections will reduce to a single inductor. If both poles are present, it will reduce to an LC circuit. So we're talking about this single capacitor, single inductor, and this LC circuit. We can reduce the losses by using a resistor. We put it in parallel with the series LC circuit. To find this value of the resistor, we can use the conductance value. The conductance value will be given by W is equals to C over Q. Q is the quality factor of the resonant circuit. And we have the same cases for the Foster's second form. I don't know if I understood it to that point. Is there any question? We take that as a no. Okay, for my example, we'll look at network synthesis. Network synthesis determines the possible networks used to obtain a certain frequency response. Driving port impedance is used to obtain the first Foster network. The driving port admittance is used to obtain the second Foster network. The conditions for Foster synthesis are: positive wave function represents a two-element kind of LC network with critical frequencies of ZS on all axes of IW in the complex plane. The critical frequencies will alternate between poles and zeros. The there must be a single critical frequency at the origin and at infinity, and all other critical frequencies must form conjugate pairs. ZS must be a ratio of an even and odd polynomial, and the degrees must be far by 1. The conditions for a realizable transfer function. These are the conditions for which we can look at this for here. These equations here. We can look at these equations to find if they are realizable using the Foster's form. The Foster's form, whether it can be Foster or the Foster's form, the first, the second Foster's form. The polynomial S must have positive real coefficients. The numerator and denominator polynomials can be divided by 1. If the polynomial is neither even or odd, all powers of S must appear. And if the polynomials are even, the other must be odd and all other odd. Okay, all this we were taught last year. If anybody has a question, you can just raise the question, but I'll just move forward to an example. The things to remember here are to represent we can represent a resistor, a capacitor, an inductor. We can have an inductor in series with a capacitor. We can have an inductor with a resistor, and you can have capacitor and a resistor. This will help in synthesizing our networks. When you take in the frequency domain, given this is R, this is LC, this is LC, this will be R, this will be SL, SWL, this will be 1 over SWC. I don't know if I'm right. Okay, sorry. SL 1 over SC. This is okay. We can use the relation for SL and SC. This is SL times 1 over SC over SL plus 1 over SC. When you simplify these two, it will be L over C over SC S squared LC plus 1. Multiply this by SC, we'll get this is L over C. We're basically simplifying such that we can remove this SC here. This is LC times SC over S squared LC plus 1. This cancels, so this is SL over S squared LC plus 1. This is the equation we're looking for. We can do the same one for this one here. This is SL times R over SL plus R. This is SLR over SL plus R. And then for the final one, 1 over SC times R over 1 over SC. Okay, now these are the equations that we will use in our Foster synthesis. You can take for an example this first equation, ZS is equals to S squared plus, this is S squared plus 2 S squared plus 1 S squared plus 3. Okay. Sorry, I think this should be okay. Now when you simplify this, it will be AS over S squared plus 1 plus BS over S squared plus 3. Now these are the equations. We will find AS and BS, and then we will use those to find the corresponding values for this, for the corresponding values of LC or LR or RC. Now in this case, we can multiply this whole equation by S squared plus 1 and S squared plus 3. The same for this side, so that it will be S squared plus 2 BS S squared plus 1. And then we can find now the value of A and B. To find the value of A, we can put this value of B to be 0. So we can put S is equals to 1. And to find the value of B, you can put S is equals to some value of here should be 0. So we can put S is equals to 0, not 0. S squared should be equals to 3, or S is equals to the root of 3. Now when we do this, we will find the value of A and B as a half and a half and a half, as this example here, 1 over 2 and 1 over 2. So our answer becomes sorry, I have to refer here. Okay, I didn't copy the question correctly, but it will be fine anyways. S squared plus 1 plus a half S squared plus 3. Now relating this one with this equation here, we can find this is it's an inductor of inductance value a half. So this here, this equation has an inductor with an inductance value of a half, and we have LC is equals to 1. So C is equals to with LC is equals to a half, C is equals to 2. So we have, so this first equation will represent an inductor of value 1 over 2 and a capacitor of value 2 farad. This is Henry. The same can be done for this side, and then that's how you get these equations. But I didn't copy the equations correctly, but that's how you do the synthesis. The same can be done for the Foster's second form, but this time we are considering the admittance values such that the capacitor will be SC, the inductor will be 1 over SL, And then we can consider like an inductor and a capacitor and so forth. These I've already highlighted here some examples already together with the workings. This should be simple enough since we did it in third year. Is there any question? No question. So
When you'll be sharing the slides, could you also include the whiteboard?
okay, yes.
So I'll continue from where Angesa has left us. I have a disclaimer though. Some of the concepts I had prepared to present are not really relevant for our scope of study. So you'll allow me to just brush through what I have, then we proceed. So on what Gesa has shared, he had some equations, and in some certain circuits, the equations will not apply because the series does not converge. So those who did German, I don't know how this name is pronounced, but he developed an equation to add convergence factors so that the Foster series can be used to evaluate other circuits. And Mittag Leffler also explains how these functions are formed. This was the function for the first reactance, Foster's first series. And this is for the second Foster form. So in comparison to the first equation, there is a convergence factor that has been added. This example will also be too complex for our scope, so I'll skip it together with the second example, but the slides will be shared. Maybe I'll just share what I found from Shelkunov's work. That is the use of his polynomial array in microwaves. So the polynomial array is a useful tool in the analysis and synthesis of antenna arrays. And this is done by representing the linear arrays as polynomials. So we have a radiation pattern over here, which defines the variation of power radiated by an antenna. And instead of steering the antenna arrays, I will display the photos of what antenna arrays look like. You can ensure that in certain directions, the energy is minimum or it goes to zero. So how that is done is by selecting the weights of the antenna arrays so that the radiation pattern has nulls in certain directions. So that means in that area, for example, if it were here, there would be no energy being transmitted So an example of that is in this illustration I have here. So these dots represent antenna arrays, and they are transmitting or receiving signals within this radiation pattern, the outer circle. So if we have a jamming signal being sent to a particular antenna array by maybe during a time of war, we can use the Shelkunov's polynomial array to take the radiation pattern to zero so that no energy will be transmitted in this direction, and therefore the jamming signal will not work on the antenna arrays. So this is an example of a 4-element microstrip antenna array. This is an example of a cell tower antenna array. Some of the arrays are used to receive signals and others to transmit the signals. So by using these polynomial arrays and the weights of the antennas to direct the radiation pattern, we can avoid interference in our signals, we avoid the jamming signals, and also noise can be reduced or completely eliminated. So this is a general form of the polynomial. Since it is not in our scope, it's just an interesting thing for us to note on how these concepts apply in the microwave field. So I will end my presentation there and invite the next person to tackle S parameters. Or any questions? Okay, thank you.
Good morning. So I'm going to do scattering parameters. So scattering parameters, or the S matrix, are used in microwaves for, wait, can you hear me?
Yes.
Yes.
So scattering parameters are used in microwaves for characterization, modeling, and design of microwave devices and networks. So a scattering matrix represents how radio frequencies energy moves through multi-port networks. So at radio frequency and microwave frequencies, impedance or admittance description of networks. You can remember from ECT we did impedance matrix and admittance matrix, the Z and Y parameters. But we can't use them here because there's an abstraction, since voltages, currents, and admittances can't be measured in direct manner in microwave frequency levels. So we use a vector network analyzer. So a vector network analyzer measures the wave reflection coefficient at a particular network port or wave transmission coefficient through a network. The directly measurable quantities are magnitudes and phase angles of the reflected or scattered from the junction relative to the incident wave. So the input is the incident wave, and the output will have a reflection at the output and at the input too. The matrix describing the linear relationship between incident and reflected waves is called a scattering matrix. So this is a picture of a vector network analyzer. Then this is an N-port network. So you can see, looking at, let's say, port 1, V2 positive is the incident wave, I2 positive is the incident network, then V2 negative is the reflected wave. So this is a scattering matrix for an N-port network. You can see the reflected the reflected parameters are here, V1 negative, V2 negative, all the way to Vn negative. Then V1 positive are the incident, then S1, S11, S12, all the way to S1n. Those are the scattering parameters. So we can simplify it as the reflected parameters are the products of the scattering parameters and the incident waves. A specific element of the scattering matrix is found as Sij is Vi negative over Vj positive. So Vi negative is the normalized reflected wave at the ith port, and then Vj is the normalized incident wave at the jth port. Then, so let's describe that. This says that Sij is found by driving port I with an incident wave of voltage Vi, and measuring the Vj and measuring the reflected wave amplitude Vi coming out of port I. I meant Vi, both are Vi, not Vj. The incident waves on all ports except the ith ports are set to 0, which means that all ports should be terminated in matched loads to avoid reflection at the other ports. It is then seen that Sij is the reflection coefficient seen looking into the port when all other ports are terminated. Also, we can say that Sij is the transmission coefficient from port J to port I when all ports are terminated in matched loads. Let's do an example. Then Ochor will look at the properties of the S matrix. His presentation has covered that. Evaluation of scattering parameters. So example, it's a simple example. So we'll find the scattering parameters of the 3 decibel attenuator circuit shown. So because this is a 2-port network, we'll have a 4-port. Oh no. The S matrix will have 4 elements. So S11 can be found as the reflection coefficient as seen in port 1 when port 2 is terminated in a matched load. So it's the normalized impedance, normalized voltage wave at port 1 over the normalized incident wave at port 1 when port 2 is 0. That's why V2 is equals to 0. So you can say that it's the transmission coefficient when port 2 is set to 0. That is so we use the impedance at the input minus the impedance at the out. The matching impedance over the impedance at the input plus matching impedance. So we can see from the circuit, you can see the combination of the 2 parallel. So we add 8.56 plus 141.8 multiplied by 8.56. When you do that, you will find that S11 is 0. And because of the symmetry of the circuit, S22 will also be 0. So we go to find S21. So we apply the incident wave at port 1, that's V1 positive, and measure the outcoming or reflected wave at port 2, V2 negative. So S21 is the reflected wave at port 2 over the incident wave at port 1 when the incident wave at port 2 is 0. So from the fact that S11 is equals to S22 is equals to 0, we know that V1 negative is 0 when port 2 is terminated at the matching load of 50 ohms, and V2 positive is equals to 0. In this case, we'll have that V1 positive is the supply voltage V1 and V2 negative is supply voltage at port 2 V2. So you apply voltage division and then you'll get V2 is equals to 0.707 V1. And then you remember to find S21, you need to divide over V1. So 0.707 over V1 gives you S21, which is the same as S12. This is 0.707. Is there any question or any clarification you seek? I guess the silence means we are okay. I'll let Ochor take over.
Hello. Good morning. So I'll continue from. I hope you can hear me. Someone could kindly give me a feedback.
Yes, I can hear you.
Okay. Thank you. I'll continue from Abel's presentation. Okay. So as parameters, as we've been told by Abel, they're the scattering parameters. But why do we need S parameters? Tony, from Abel's presentation, Tony Oloibe, why do we need S parameters? Tony or Makana, why do we need S parameters? From the presentation by Abel. Okay, we need S parameters because you realize at low frequencies, we can characterize a device by using the impedances, the admittances, Z and Y. But now at high frequencies, there's an issue, and Abel has actually told us the issue at high frequencies where we can't really work with the impedance or admittance. Maybe Clement could tell us the reason. Hello, someone has a question. I can't really see the question. Maybe you could unmute. Clement, kindly tell us why at high frequencies it becomes difficult to use lumped parameters model. If Clement could be in the meeting. Okay, let's just continue. At low frequencies, you realize the wavelength is let's say large. So basically, you can consider your circuit as an entity, a complete entity. But when you go at high frequencies, it's quite difficult to do that because now you have, for example, millimeter waves, and a resistor and inductor will start behaving not as a lumped model. Okay, that's why we need S parameters. That's from Abel's presentation. So S parameters, you can take it to be like a black box where you put something in and then you get what happens. You can predict the behavior of this black box. So basically, S parameters is like a black box of parameters where we can know. From Abel's presentation, he had a network analysis, better network analysis. So the black box will contain a resistor. I hope I'm still audible because I think the internet is bad. Maybe someone could tell me if I'm still presenting. Okay. So the black box could contain a resistor, a transmission line, or an IC. But in the case of S parameters, it could be a transmission line, considered as a transmission line. Okay, so let's look at these. For example, these are two-port network. You have port 1, you have port 2 as a black box. And you can consider these ports as lines. And as parameters, you can enter a frequency into one port and then you study what happens at the other ports. When you put an incident wave, you can get a reflected wave, etc. For example, here, you can have now a wave that's reflected, another that's transmitted from here when you enter at port 1. Okay, from Abel's presentation, we've seen him representing as S11, S21. Maybe someone could tell us what S11 means. I'm picking a random person. Denver, what does S11 mean? Okay, S11 refers to the signal reflected at port 1 for signal incident at port 1. So you enter a wave at port 1, that is A1, and then you want to look at the signal. Sorry, you look at the signal that's coming out of port 1 due to the input A1 from this statement to the signal reflected at port 1 for signal incident at port 1. What about S21? S21. For S21, we want to look at signal exiting at port 2. Here, you see the signal exiting at port 2, which is B2, over the signal at A1. So for the signal incident at port 1. So S21, basically, you're looking at B2 over A1. Okay, so S21, someone could ask, why not S12? It's S21 because it's a convention to always refer to the port that's responding. So the port that's responding is port 2, so that's B2, and the input port is A1, so that's why it's B2 over A1. Okay, so as parameters, let's look, for example, at S22. S22 could be Victor Baraka. Could you tell us what S22 refers to? Or maybe just say you can still hear me because I might start talking to myself. S22 now is the ratio of B2 over A2 because B2 port 2 is the responding port, so B2, A2 is the where you're putting it, A2. So basically, kind of this S22 is let's say a return loss because it's a ratio of the reflected of reflection. Let me say that S12 is the signal exiting at port 1 because that's the responding over A2, and A2 is the input, the incident wave. And this is just an illustration of what a return loss could be. It's like you transmitting and then the reflection. Okay, so for a two-port network, you've seen S11 B1 over A1, S12 B1 over A2, S21 B2 over A1, S22 B2 over A2. Okay, and take note that this is the responding, this is the where we're inputting the signal. Okay, so after that discussion, maybe someone could ask, why do we need S parameters? Maybe someone in the chat could give me feedback. Why do you think we need S parameters? Abel mentioned it. I also think I did. But anyway, let's continue. So we've seen you can, when you input a wave, you can see the reflected wave, you can also see the transmitted wave using S parameters. And S parameters can be complex. That's why sometimes you can refer to them as complex scattering parameters. Demonstration of transmission, this is incident, and this is reflected. It's just a visual representation. S parameters, of course, depend on the network, they depend on the frequency, they depend on the load impedance and the source impedance, etc. For example, here you can see is load impedance, source impedance. Okay, so to represent a two-port network, the S parameters. So these ones are the output. This is the S parameters. This is the input. So it's just a matrix: S11, S12, S21, S22 times A1 times this matrix give you the output matrix B1, B2. So S12, S21, S12, S21. These of course are transmission coefficients of the S parameters. S11, S22, they are there. Maybe someone could tell me, Kimaiga Rebecca, what is S11 and S22 referring to? Am I in the meeting? Okay. Oh, okay, I'm in the meeting. Okay, someone could tell me what S11 and S22 refer to. George Mwangi.
Those are self-reflections on the port they refer to.
Yeah, thank you. They are, yes, thanks. They are the reflection coefficients. They refer exactly what George has said. And some matrices could be symmetrical. A symmetrical matrix has symmetry about the leading diagonal. So for example, S21 is equal to S12. That's a symmetrical two-port network. So these, when they're equal, it's symmetrical. A transmission line is an example of a symmetrical two-port network. Okay, so on your right, this one we were shown by Dr. Moyama last year's electrodynamics class, and George presented on it, the hybrid T. If you can recall, it was like a week ago. Yeah, so you can have larger networks, not necessarily two-port. You can have three-port, four-port, but now the S matrix will be defined by n squared. And yeah, you can use these subscripts I and J, where J is the port that is excited and I is the output port, just as Abel had said. So I is for output, J for input. Okay, this is an example of a four-port network. This is called a quadrature hybrid coupler. Here is a representation of it in two dimensions. So port 1, port 2, port 3, port 4, here's the matrix. Output B1, B2, B3, B4, the S parameters S11, S12, S13, S14, S21, S22, S23, S24, A1, A2, A3, A4. Yeah. So properties of S parameters, I'm just going to look at three. So for of course, this one you've seen is a square matrix order n by n. This one you've seen order n by n square matrix. And then number two is the identity property. S times S conjugate gives you identity. Yeah. Symmetrical, Sij equals to Sji. And a network is reciprocal if S is equals to S transpose. Basically, reciprocal is telling us that, say in a simple term, if you look at the network in the reverse direction, you'll get the energy flow being the same as how you are looking at it in the previous way. So for example, if I input energy this side of the network, port 1 for two-port network, if I do the reverse, it should be the same. So S is equals to S transpose. So here, this is S matrix. If you transpose this, of course, you take this, put going like that. Take these S21, S22, S23, S21, S22, S23. Take that, go like that. And then A network is lossless if S transpose times S conjugate is equal to identity matrix. But this, if you open now, S transpose, I don't want to do that right now, but this statement can be written for a two-port network. For example, S11, the magnitude squared, plus S12 squared is equals to 1. So basically, row, every element of a row, for example here, S11 squared plus S12 squared plus S13 squared is equals to 1. If this, you open up this expression, you get to this conclusion. So if you do this row, for example, S31 squared, the magnitude plus S32 squared plus S33 squared, you should get 1. So that's what this is saying. And then multiplication of rows, that's another property of S parameters. But for now, let's put this one in our microwave lobe in the brain, that a network is lossless if S11 squared plus S12 squared for a two-port network is equals to 1, and symmetrical, of course, and reciprocal. So reciprocal network, symmetrical, square, and identity, because we'll use them for a question that's coming here. So here's a question. Question 1. The S matrix of a two-port network is given by this. So fine. Is the network reciprocal? I've not done it. You can see I've not done it. So you're supposed to, you guys are supposed to do it. So is the network reciprocal? Lennox is mine. What's the condition for a reciprocal network? How will you know a network is reciprocal? Here. Here. S is equals to S transpose. So what should I write for S transpose? Okay, maybe Victor Baraka. George, maybe you could help us. Is the network reciprocal? How do you know two matrices are equal? Rebecca Kimaiga, how do you know two matrices are equal? If we did this in numerical method or in high school, matrices. Two matrices are identical if this is equal to this, for example, this, that, but you can see quite clearly they are not equal. So basically this network is not reciprocal. And lossless, someone can check if it's lossless. The condition, how you check for that, is what you've done here. S11 squared plus S12 squared should be equal to 1. Victor Baraka, is the network lossless? If you take 0.15 squared plus 0.85 squared, what do you get? Do you get 1? If you get 1, then it's lossless. What do you get? Antonio Loibe.
Not lossless.
Yes, thank you. Not lossless. Okay, and then number 3, if port 2 is terminated with a match load, find return loss at port 1. Okay, so what does a match load tell us for a network or for our analysis of a transmission line? Clement.
Clement is not in the meeting.
Okay, anyone who is in the meeting, you could tell me what, if we have, for example, here A1, this is A1, and then you have here B1, and then here you have A2, and here you have B2. So what it tells, if you terminate it with a match load, so this is match load, so let's say it's Z node. So basically match load, you remember from these, I remember it's these, ZL minus Z node, ZL plus Z node. So you will get a 0, of course. So that means B2 will be 0. And when you have B2 equals to 0, I hope you remember the questions we wrote. We had B1 is equals to A1 S11 plus plus A2 okay. So sorry. A2 should be entering here, and B2 is the one leaving. So if we have from here, we can see quite clearly there is no reflection, so we'll have A2 0. So this time we go, and that means to get the return loss at port 1, which is S11, will be B1 over A1. So you should do B1 over A1, but basically it's S11 this term. And then you should do 20 log 0.15 to get return loss in dB. Someone could do that. 20 log 0.15.
16.5.
Yes, 16.5 dB. Thank you, Tony. And now for number 4, I'll just give you an idea, but you guys will do it. I'll send the answer maybe later. If port 2 is terminated with a short circuit, now if you have a short circuit instead of a match load, a short circuit, for example, that means what entered this port will go like this. So that means B2 will be negative of A2, and then you replace in the equations so that you get the new B1 over A1, and then you do 20 log that. And you'll be able to get an answer which is, let me check what was the answer so that you can know if you've done it correctly. Sorry, Tony, what did you say 20 log 0.15 is?
Oh, so if it's 16.5, ni iko na negative hapo mbele.
Yes, negative. Yeah. Okay, for this, you should get an answer of, when you do it, of course, negative 6.93 here, negative 6.93 dB. Okay, so the takeaway from today's discussion is that a network is lossless if that condition S transpose times S conjugate is equals to the identity matrix. But if you open up that, you will get that row wise, if you do S11 squared, S12 squared, but if you have a 3 by 3, you'll add the S13 squared, you should get to 1. And then for reciprocal, S is equals to S transpose. Okay, thank you. That's the presentation we had for S parameters. If anyone has a question, if anyone has a question, you could ask. Thank you. Sefin, I'm done. I don't think we'll have time to go to the next one today.
Okay. So there's still a presentation left from your group.
Yes.
Okay, we'll continue with that tomorrow during the class. We can end today's class here. We'll continue tomorrow.